So for the last segment of the day, we'll have Andreas from University of California, San Diego. He's going to give a presentation on powering Ember molecular dynamics simulations with GPUs with SYCL. So, where's...
All right, great. Thank you for the introduction, and thank you for giving me the opportunity to present our work here. So I'll basically do something similar like in the previous talk. I'll talk a little bit about Ember first to give you an introduction what it is, and then how we ported it to SYCL and where we're standing nowadays. There we go. Yeah, first of all, I would like to say thank you to a few people. I've been working very closely with Intel, in particular Guochuan Chen. So he's the person who's done all the groundwork. So he's been doing most of the porting work. And he had some help by other Intel software engineers. And then Ramanujam and Kitur Ganesh for some of the project management and funding from Intel One API Centers of Excellence program. And so just to give you a brief introduction, what is Ember? Sometimes, you hear people talk about Ember. It's two things. It's a set of force field parameters. I'll briefly come back to what that is, but basically it encodes, the interactions between atoms and molecules, and in particular for biomolecular simulations, all sorts of like different proteins, carbohydrates, and similar things. It's also the name of a molecular dynamics software package. It's really for biomolecular simulations. It's been around for over 30 years. So it's what you would say basically legacy code. There's actually approximately 50 principal contributors to the current codes, and it's distributed in two parts: Ember Tools, which is entirely open source and GPL free, and then Ember, which has the high performance MD program, PMMD, that I'm going to talk about today. That's under academic licensing, so it's free for nonprofit and academic research. And it's actually really very widely used. So we have a big user base in academic and industrial research. Steadily growing user base, installed in all major compute centers. It's often used also as one of the codes for acceptance tests. And in particular, has been growing popularity with the release of the CUDA code that came out in about 2010. So it's been a long time that we had the CUDA code. And if you look at the citation numbers that we have, so we're getting about 250 or more citations per year. So there's a high scientific output beyond what is done in industrial research. And of course, I don't want to talk much about this, but basically all the development that we had in molecular simulations, has gone hand in hand with all the hardware developments over the time. And so it's very important that, we can stay close to the metal, that we can keep, our codes having good performance on current and future hardware. So one of the ideas basically moving to one API and trying to use one API is maintaining that trajectory. Here's another plot just showing popularity of molecular dynamics simulations in general. So it's been steadily increasing. It's one of the most widely used simulation methods for molecular systems, and in particular Ember. So there's many different codes. And there's a handful of famous codes, including Ember, Gromex. You have heard today, I think, or some other people mention. There's Charm, NAMD. It's among the most popular codes. So it's important to have high performance because many people are using it, and we don't want to waste a lot of compute resources. So typical applications that we have is all sorts of biomolecular applications. So here you see the cover of manuals from the last 6 years. Well, actually 2023 is missing, but I didn't update the slide. It's all sorts of like interesting biomolecular systems. And so it helps us understand how life works at the nanoscale, basically. It's used in computational drug design. That's why it's interesting for industrial applications, pharma industry in particular. And so we can understand structure and function of biomolecular systems, protein folding, enzymatic reaction mechanisms, stability of protein in drug complexes. And like I said, it's often used in the drug design pipeline. And so it's a molecular simulations code. And just as a brief background, so what we like to do, I'm a chemist by training. And so I started out using quantum mechanics to solve Schrödinger equation, electronic Schrödinger equation. So that's not what we do in Amber, right? So, but that's basically with a way in which you can describe interactions between atoms and molecules. That's highly expensive and very numerically intensive. I could talk about in a different talk because there's another code that I develop where we do that. But instead, what we're doing in Amber is we're using so-called molecular mechanics force fields. So it's like a ball and stick model of atoms and molecules with a very simplistic form. So the interaction energy, the potential between the atoms that you see here is just some harmonic potentials. And then the expensive part is the non-bonding part. It's really the particle-particle interactions. It's like Coulomb's law, basically. It's really trivial. But if you do it right, you can actually get the right physics out of these models. And so ideally, what people want to have is, not only something that's fast, but also accurate. But we'll focus on the force fields for now. And that's what we have implemented in Amber. And if you do it right, you can actually get nice chemistry and physics described. And here's an example of a molecular dynamics simulation. So what happens, here's a representation of an enzyme, for instance, and you can see water molecules moving in here. This was a publication I was involved with a few years ago. And you see that, we simulate basically time steps. And at each time step, we need to compute those interactions that I have been showing you before. And just to give you an idea, so the relevant timescales, they span about like 16 orders of magnitude. So the time step in terms of, what we simulate in that molecular system is on the order of femtoseconds, because that's the vibrations in molecules. And to discretize, Newton's equations of motion, we cannot go to longer time steps. But all the physics happens, what's interesting, on the nano microsecond or longer time scale. So we want to simulate a micro to milliseconds of that molecule. But we take femtoseconds time steps. And this means we need hundreds of millions of time steps. Or we need less than a millisecond of wall clock per time step. So all those interactions between hundreds of thousands and millions of atoms need to be happening in a millisecond for any of this to be actually really practically useful. And if you do this right, you can get very high performance in GPUs. And that's where, a lot of molecular dynamics simulations have become much more useful over the last decade. And so this is already older. Amber 18, basically 6 years ago. But you can see the performance that we got with our CPU implementation. And you could argue, you could, increase that performance. But it was a reasonably, tuned code. And that's basically a simulation time in the time of life of a molecule that you can get in 24 hours. So nanoseconds of simulation per 24 hours per day. And you can see that on both on data center, but also on gaming GPUs, you can get like orders of magnitude higher computational throughput. And that has really transformed the way that people can do science with molecular dynamics simulations. And so what's the motivation for us to move away or, to use SYCL when we have a very successful and popular CUDA code? Obviously, I guess I don't have to tell you, but the reason is really you want to enable Amber to run on Intel GPUs, but not only, it's an open standard, so it's nice to have that. We hope to attain performance portability in one way or another, because we could use different backends for NVIDIA, AMD, and Intel GPUs, and hopefully a single code base is also more maintainable. Of course, the Intel GPUs give us good floating point performance, and there's good memory bandwidth and similar things. Don't want to delve into details of the hardware, but that's some of the motivation. Now, what were the challenges? So if we look at the code, the pmd.CUDA code, so that's where we started out with. So we have a legacy CUDA code. It consists of a large set of highly optimized kernels for these particle force calculations. Time stepping, temperature, pressure control. There's lots of algorithms with which you then actually can connect, the microscopic simulations to macroscopic quantities that are of interest, for, drug binding energies and similar things. And then there are many, many different code paths for all sorts of different approximations that you can make, like different solvation models, different types of thermostats and barostats. and enhanced sampling algorithms, ensemble simulation methods with MPI, et cetera, et cetera. Then there's also some technical details. We have multiple precision models implemented that we like to keep. There's like a mixed single precision and 64-bit fixed precision for accumulation, data accumulation, and reference code with a double precision, so 64-bit floats and fixed precision implementation, and single and multi-GPU support to enable ensemble simulations, CUDA intrinsics, PTX inline assembly code. And so if you look on the right, this is just to point out, if you don't do things right, if you use 32-bit floats where you shouldn't use them, then the simulations, of course, they look okay on short timescales, but things blow up. And there's a lot of effort that actually went into that over 2 years, experimenting with different kernels and optimizing them so that we can run with optimal performance also on gaming GPUs, right? That's another thing to keep in mind. Data center GPUs are very expensive, and what really made a big breakthrough is, a lot of PIs, you give them the code and they have a graduate student in the lab, and the graduate student can run on a $500 GPU and actually get some science done. It's not to underestimate, right? The power of being able to do that. And yeah, so there's a lot of code history, many years of initial development, decades of contributions, and it's not easy to rewrite from scratch. So there's basically no way to start from scratch. So instead, we start with the CUDA code. And so it's not only CUDA, it's originally Fortran 90 code, so all the drivers still Fortran code. So it's a mix of Fortran and C++. And non-CUDA code, but the CUDA code itself is, I don't know, it's about 25,000 real code lines and about 459 CUDA kernels and 282 CUDA device functions. So there's a lot of code that needs to be ported. But at least we don't have a million line of kernels, right? The kernels are shorter. And so what we did is really start with the CUDA code using the DPC++ compatibility tool. So basically what is now Cyclomatic. And then convert the intrinsic and assembly code, fix compile time errors and warnings, and that takes some time. So it's not done in a few months. So there's like 2 years of effort. And then debug and verify functional correctness, and then of course profile and optimize. So far only in Intel discrete GPUs. So the status currently is, so we have a base of the release of Amber 20. So that's a 4-year-old code base, but project started in 2021. Amber's released every 2 years. And we just wanted to work with a stable code base with initial goal to get it working on Intel data center GPUs. And then now we're working on feature completeness and for future Amber releases. So ported everything with Cyclomatic basically, and then added a kernel by kernel CUDA to SYCL verification framework to make sure that if we stick the same thing into the kernels, same thing comes out. And so we have basic MD running with thermostats, barostrats, restraints. So there's some features missing, but much of the basic molecular dynamics works, and correctness was verified. And we have a test suite, so this automatically runs now. And it works on Intel Max series data center GPUs. And yeah, I like to leave in when I talk about this that, CUDA and SYCL kernels are quite similar in some sense. That of course, it looks different, and there's, in particular, if I show something like this to a CUDA developer and they look at this, or, when I say CUDA developer, I'm talking about domain scientists who know a little bit of CUDA. And they're like, oh, there's many more lines on code. It looks more complicated. Oh my God, right? So this is some of the convincing that we have to do. But, if you look at the kernels themselves, they're, obviously very similar, not too much difference. So if we test the code, you can see, I don't want to talk about the details of the physics, but basically numerically it reproduces the reference CUDA implementation compiled and with CUDA and run on NVIDIA GPUs. So, you can't reproduce step by step. There's, some numerical differences always in there, but if you overlay the CPU code, it will have the same differences. But, the statistical averages of all the properties that we compute from a molecular dynamics trajectory match. So everything is numerically accurate. And so we looked at performance. Here's a benchmark setup. This is a virus. This is a standard benchmark. It has about so STMV, satellite tobacco mosaic virus. You have to think about it. It also has water around itself, and then it is under periodic boundary conditions in the box. It's about 1 million atoms. And then we looked at performance optimizations guided by Intel OneProf, OneTrace, and vTune. And so there are several performance optimizations that we had to do. So some of the most important ones are in the non-bonded force kernels. So those are the kernels to compute the electrostatic interactions. There are many different types of those, depending on the type of simulations. And just let me point out a few things. For instance, we're using subgroup shuffles with variable lanes in the CUDA code. And that's currently inefficient in at least in, the PC++ implementation. So if you look at this, what we're having here, for instance, you look at this, it's like we compute the distance between two atoms, and each thread owns an atom and knows the coordinate of one atom, right? And its charge. The next thread, another atom. And so we just basically get the values from register from the other thread and then take the difference. And so we have the distance xyj and similar things. And so we just, in this case, we replaced it by using shared local memory to get back performance. I'll show some data about that. It's very similar when we store back the forces. Instead of using a shuffle operation, then we're working with shared local memory in this case. And so some of these things we had to do. Some more simple things like ND ranges, which, coming from the translation were fixed to 800. I don't remember why, but, that doesn't make sense. And then so you increase it to reach a good occupancy. We had to do some memory space casting, where we had inefficiencies in global atomic operations. Right now, just using a pointer alias outside of the kernel to simplify the pointer address and avoid dynamic address space checking and casting overhead. And then, some other things like sorting algorithms, using more efficient sorting algorithms and implementations like eSIMD-based radix sort implementations. And so if we look at some of those things, here's some profiling data, for instance. We can see that, we have a lot of stalls. There's pipeline stalls in this kernel that I was talking about here. So about 70%, 73%. Also memory bandwidth is not fully used. And of course, the thread count relatively low. And after fixing all those things, we get much higher activity, so much less stalls. Stalls are reduced, and memory bandwidth is much higher. And in terms of timings, how that looks like, so you can see this is this kernel, but there were other kernels as well. So you see the runtime of a kernel for this big system. And it's much slower than, say, the kernel runtime of the CUDA kernel on an NVIDIA GPU. And after the optimizations, it looks much better. So total runtime for the sampling here, over 2x speed up for different kernel times. And the overall performance evolution then looks like this. Initially, this is a comparison. 100% is the code running on an NVIDIA H100, the CUDA code. Initially, we had a performance of 20%. And, after all the optimizations that we were doing, we reached, that's a half a tile of an Intel GPU Max 1550. One tile, so half of the GPU, about 50% of the performance, which is pretty nice, I think. And you can see in particular, you start at 20%, go up to 52. That's, I think a nice result. And then for two tiles, we're looking at, yeah, what I wanted to say is basically here's some kernels here. That's an implicit scaling. So, it's actually getting slower running on 2 tiles. So we had a very bad scaling. If we treat the whole card as a single device, so instead you have to treat them as 2 devices and use MPI-based explicit scaling. What we do is optimize the force reduction across 2 tiles when we compute the forces with a point-to-point communication, really, instead of like doing some reduction algorithms that lead to a lot of traffic. We just send the data, reduce on 1 tile, and send some of the results that we need on the other tile back on the other threads. And similar thing. So lots of data on there, but I think the important piece is, if you compare running on an entire data center H100 GPU and this is running on an entire Intel GPU Max 1550. So we don't get up to the 100% that you might expect because we get about 50% on running on a single tile, but decent performance, I think. And for everybody else, you can just run on a single tile. And if you have throughput simulations where you run many simulations, looking at this is the overall summary. So running on a single tile, about 50% of an H100, 2 tiles, 80%. But often what we have to do is we run in a sort of like way that we have to run thousands of simulations, or we have simulations that are not tightly coupled, where we're running simulations and ensemble simulations effectively, where only every few hundreds or thousand steps some data is exchanged. That can run very efficiently, say on a half a GPU or 1 tile in this case. So a pretty nice performance. So I want to just have 1 or 2 slides and then I'm done about talking about the future. We're currently catching up to Ember 24. We started with Ember 20, and there have been many changes to the CUDA code actually between Ember 20 and Ember 24. And so we started from scratch with Ember 24. This was easier than backporting the changes. And so we hope that we don't have to do that in the future. We're working on feature completeness. Most of the code is ported, but needs testing, profiling, optimization. I see some people smiling in the audience, but this was really easier in particular because the person who's done this before knew exactly what he did. When that person is gone, we can't do this again, right? But portability and performance portability is something that I'm very interested in and to looking at. So we want to get the code to run on Intel gaming GPUs. It does not work out of the box. Can talk later about that offline if you want. NVIDIA GPUs, AMD GPUs via CUDA and HIP ROCm backends. I'm very interested to see how well the code works and what we have to do to get it to work and performant. And I think it's very important, in particular for the code sustainability, because we cannot afford 2 code bases. So we have a CUDA/HIP code currently, and now we have a SYCL code, right? And we need to convince developers to switch to SYCL. And the developers are not computer scientists. They are domain scientists like myself. I'm a chemist by training. And so I learn as much as I can, but I hear a lot of things that you talk about that I have no clue about, right? But it's normal, right? I understand the physics in the code. So the future developers are mostly domain scientists, right? And they want to solve scientific problems with as little effort and as quickly as possible. The current generation is familiar with CUDA. That's what it is. And so, it is hard to convince them to face a learning curve, to adopt new technologies, and they need good arguments to switch, right? So I think the requirements are feature completeness of the code. We're getting there. And the performance needs to be there, right? So that the PI tells them, well, if you implement something, use that code base, not that one, right? Or at least try to get into both and so on. Otherwise, one may die at some point. So that brings me to the end. So Ember is a widely used biomolecular simulation software, and we've used it Intel One API tools to port it, the high performance CUDA engine to SYCL, optimize the SYCL code. It's numerically stable and shows pretty good performance, I think, on Intel data center GPU hardware. And so we're working on advanced simulation techniques, porting those, that we get everything ported over. That's almost done or close to. And then performance portability in order to make the code usable for the community and hopefully sustainable for the community. And with that, I'm at the end of my talk. I hope I'm pretty good in time. And so thanks for your attention. I'm be happy to answer questions.
Hi, so I've been working closely with the Chromex developers, and what they've always communicated to me is, hey, so SYCL is great, so our kernel performance is roughly on par with, you know, what we have for HIP or CUDA or so, but we're seeing some runtime overheads, and this is, for example, related to the fact that in SYCL you always get an event return from the kernel, whether you want it and use it or not. And I wonder if you're encountering similar issues in your code base regarding runtime overheads.
I cannot answer that question because it's something that I haven't looked into. So I've not looked details of these profiles, and but it's something that I want to look into, and in particular in comparison then also to, you know, the CUDA and the HIP implementations that we have. And I don't know, some of this might be, I don't know if the CUDA graphs will help with that.
Perhaps,
you know.
Thanks.
So first, a comment on Axel's question. If you're curious about that, I recommend a talk tomorrow. Secondly, you mentioned you had a remark there about issues running on Intel client discrete GPUs. I'm assuming that's over FP64 support.
That's right.
Okay. Hopefully that will be fixed in the future.
Yes, right. Yeah. But it would be nice, you know, I have some Intel ARCs lying around, and I have some students that, you know, I want them to play with this stuff. So, and I have to say, okay, well, we got to go to the Intel Developer Cloud and similar things there.
Two questions. One, for the results you showed with H100 or also maybe with A100, were those running one MPI rank for the GPU? Okay.
Yes. Yeah. So our code for most instances and purposes runs in, you know, the single threaded one MPI rank on a single GPU, with the exception of, you know, these ensemble type of simulations.
Then I don't think you showed results for like the MI 200 or that also has two.
No, I didn't. So
okay.
I mean, we have the code running on AMD hardware, and but you know, I actually haven't tested it myself. So
okay.
There's on a roadmap to test, but you know, the upcoming release will actually have a HIP implementation that is in the official release. It's been taking some time. It's been about 4 years, I think, that it's been a patch. And but yeah.
Okay. So now a serious question. So for Amber 26, and you were getting onto this, how do you, I guess maybe today, do you have a CPU only version?
We do, and you know, everything that works in the GPU is supposed to also work on the CPU,
So,
but nobody actually runs the CPU code.
Okay, I was going to wonder, like, how do you guarantee even the physics is the same between those two? Is the developer responsible they have to put code in both places?
Yes.
So it's the plan for, I mean, assuming that you can't have just SYCL, people have to put the same code in both branches?
Yes, it has happened now because nobody actually runs on the CPU anymore. For production runs that, you know, advanced features, some students or postdocs, they basically refuse and say, no, I'm just going to put in the CUDA code and I'm done. Publish my paper and I move on.
Yeah.
So, but almost everything is in the CPU code, reference code.
And so then it's just going to be enforcement by you or others to say, oh, someone submitted a patch to add CUDA features. You have to also port those onto SYCL.
Yeah, that's right. So usually we expect that, you know, the tests, you know, everybody who adds some new features needs to add tests to the code. There's a very large test suite that, you know, it passes with a, you know, serial code, the MPI code, the CUDA code and the CUDA MPI code.
And then based on your text, I assume you don't have a dedicated HIP branch. You just use the translation at compile time to convert.
No, there's a SYCL, I mean, it's not at compiled.
No, for HIP, you said CUDA/HIP.
Oh, right,
Do you have a HIP set of code, or you use the compile time, you translate the CUDA to HIP?
No, we have the HIP code.
Okay, so
but
you have
there's just like macros in there, and it's, you know, effectively most of the code is identical to CUDA, right?
Okay. So there is some places that you might need to also change for CUDA, HIP, and SYCL currently.
Right, but you know, what you put into CUDA effectively you have in HIP already. So
All right, I'll be interested to see how you get on in 2 years. Because I think this is the big thing for all these codes that move to GPU, how they support multiple GPU architectures.
right.